Yeah. Yeah. Yes. So yesterday we have discussed about the two-dimensional diagrams and then some 3D diagrams, and then we discussed about the pairwise diagrams, that is phase using phase function. So we have visualized more than three-dimensional diagrams, that is using pairwise display diagrams. Okay, fine. So after that, so we did some little bit correlation analysis, and we have verified whether the correlation is significant or not, and then we fitted a small linear regression model, that is simple linear regression model also we have fitted. Okay. Mm, and also we have fitted multiple linear regression model, also MLR. Okay, so when there are more than two independent variables, and then if you want to estimate a particular dependent variable based on more than one independent variable, then we are going with multiple linear regression model. Okay, and then yesterday the last, maybe some people missed this one. So for example, let us take, I will take this plot of weight comma mpg. Object weight is not found. Okay, then we have to run again. So I'm going to attach my data set. Let's just, I have attached my data set, empty curves. So now if I draw this diagram, yeah, so now this is the diagram we got, a scatter diagram between weight and mpg. So we can understand that there is a negative correlation. Now what I'm going to convey you people is nothing but, so just where I'm drawing one regression line on this plots. Okay, so if you want to draw a regression line, this is the code we have to write. So AB line is a line we can draw a trend line on the scatter plot. Okay, SLR is nothing but a simple linear regression model. So using this SLR, so the line will comes from the fitted regression model. Okay, so just I'm running this one, and this is a color, and this is line type. Okay, uh, object SLR not found. So it is asking again. You need to run this SLR. Okay, fine. So I will run this SLR. Yeah. Now again I will draw this AB line. Yeah. So this is the line where I said is fitted. L line with this line type is 10, and that's why we got some dotted lines. Okay, I will take a LWD line width, let us say 2. Some thick line we got. So this is the line, so fitted regression line for the uh, simple linear regression model. Okay, so just 2D plane. So weight and mpg. So I have taken a scatter diagram, and this is a fitted regression model. So from this model we can understand that, so some observations are above or some observations are below. Finally, if you take the sum of these observations, some of the error observations definitely will get 0. Okay, so that is the one of the property for a regression model. Sum of errors is always equal to 0. Okay, this yesterday at the last I performed, maybe some people missed it, just I recall this one. Okay, fine. So now we'll go today again. Let's save this one. So day 5 will go with our script. So see, I will take the same commands here, mlr, copy here, I will paste. Now see, for example, if I'm going with the correlation analysis and the same commands what we have taken here yesterday, this is one correlation we got, right? So I'm taking this copy and pasting here. So I will discuss, I will give you full description about this regression model today. And once we complete immediately the regression model, then we go for a testing part also. So based on time limit, we'll kind of discuss that testing of a testing part also. Okay. Yeah, fine. So just what I'm doing here I'm going to calculate the correlation between all the variables, that is all the continuous variables in this empty cause data set. This is yesterday we performed, right? And round is a function which will be useful to round the our decimals. Yeah, now if I run this one, now what will be the values in the CC? Yeah, so this is my correlation values I got. Now see here, if by taking this data, by looking this correlation matrix, now MPG is having, if I want to estimate MPG based on these independent variables, now see, some are independent variables are significant, some are independent variables are not significant. Okay, see, mpg is my dependent variable, and with this, so displacement is negatively 0.85, and horsepower is 0.78, and drag is 0.68. And here some correlations are significant, some correlations are not significant, and sometimes some significant correlations may be showing effect on your MPG, or sometimes it may not be showing some effect on your MPG to estimate mileage of the cars. So these type of situations occurs. Now what I did here, simply I have taken a linear regression model. So MPG is my dependent variable, and I'm going to estimate based on their weight and horsepower. The two variables I have considered here. Here, one question is that, so how to select which variables are important for our regression model? For example, if I want to estimate the mileage per gallon, so MPG I want to estimate based on, I have 11 variables that we know, right? There are 11 variables in our data set. Now, in this data set, how to select a variables which are important to fit a regression model, or how to select, if I select MPG, for example, MPG I want to estimate, then remaining 10 variables will be there. Total 11 variables. Out of that, if I take MPG separately, I want to estimate MPG, that is Y, based on many independent variables. There is remaining 10 variables. Now, in these 10 variables, which variable is important for us to estimate our mileage? That you have to decide. That is the main part in the regression model. Selection of the variables. So which are the variables are important for us to fit a regression model? And if I take which variables, then how much percentage I can explain the variation within the dependent variable. So like that is one separate procedure will exist. That is called variable selection procedure. So what are the variables are required, or how to select the variables for to fit our best regression model, that we have to learn. See, by taking all the variables, let us say this simply multiple integration model. Let us say I will copy this. This is we perform essay, right? Let's go with. So instead of this one, let us say I will keep dot. So what we'll do one thing first. Let me explain. Let me give you an output for this. So just I'm running this MLR. Now what about the MLR? See, multiple linear regression model is fitted with the two regression coefficients. That is, one is weight, another one is horsepower. So with these two variables, I fit a regression model to estimate the mileage of a car. What the accuracy we got, around 81%. So 81%, I can explain the variation in dependent variable based on the given independent variables, that is weight and horsepower. So this is we got. For example, let us take, instead of taking all the variables, these two variables in the analysis, just give a dot here. That is MPG tilde dot. What is the meaning of this dot? Is nothing but, so other than MPG, take all the variables into your model. That is the meaning. Instead of typing all the variables, let us say weight plus horsepower plus drag plus cubic plus volume surface plus automatic plus, like if you instead of taking all the variables, instead of entering all the variables here, just you can keep a dot. The dot is nothing but in the data set. So we have mentioned data equal to empty cars. No. So in this data set, other than MPG, what are the variables are available? All the variables will be considered to here. That is the meaning of dot. Okay. Now if I run this multiple integration model, MLR, if I run this one, now see what are the output we got in MLR. Just I'm selecting MLR and I'm running this one. Yeah, see this one. So there are 10 variables are there other than MPG. That is, one is intercept, we have 12.30, and cylinder minus 0.11 regression coefficient, displacement, horsepower, drag, weight, cubic, volume surface, AM, gear, and carb. So based on these 10 independent variables, I'm going to estimate the mileage of my car. Okay. Now what the accuracy of this model will check. Now, if I click the summary, see in the summary, we are calling coefficients. Here we can see the coefficients. See estimated value. These are intercept. These are the regression coefficient values. That is beta naught, beta 1, beta 2, beta 3, and so on, beta 10. And this is the standard error for the estimate of these values. And these are test statistics. And here you can see this one. All p values are greater than 0.05. What is the meaning of 0.05 greater than? So there is a significant, there is not a there is no significance of the parameters. See, somewhere we got a dot also, 0.063. Weight, now weight becomes insignificant. Earlier in the previous model, we have taken weight and horsepower with a regression model. In that case, weight is highly significant to estimate our mileage. But whenever considering all the variables into a model, then the weight is become invalid. This is effect from the other independent variables. Okay, so due to that, so my regression coefficient, the regression parameter weight is showing some insignificant, and also the remaining way parameter values are also not significant. See, all the p values are more than 0.05, and here you can see this one multiple R square value. So it's 86, but our adjusted R square is only 80, which means that see adjusted R square value is low 80, but multiple R square is 86. Earlier we see the output. Where is the output? Here you can see. So multiple R square is 82, but adjusted R square value is 81. Here nearer. But once I added all the independent variables into model, I said right, if I add new independent variables into the model, variation will be more. So if the variation will be more means automatically see multiple R square values increased 0.86. But the adjusted R square value, see earlier is 81, now it's going to downwards 0.80. So I said, no, what is the advantage of this adjust R square value? So adjust the advantage of adjust R square value is nothing but, so whenever you are adding a new variable into model, if the new variable is really relevant or important to your estimate your y, then the adjust R square value will increase. Otherwise, will not increase. See, because of adding the many independent variables into model, so many independent variables are not contributing because we know the correlation is not significant for some variables. So without taking other consideration, if you take all the variables into model, again you will get the loss of fit, lack of fit of the model. You will get. Sometimes you will be overfit also. So overfit, lack of fit problems will rise. Now in such a situation, we have to select what are the variables which are correctly significant to estimate our mileage. This question generally will occur in the nature. If you go for any real data set, for example, you may think that, yeah, so this is my target variable. So I want to estimate this target variable, or I want to predict this target variable based on independent variables. Now I don't know whether the rest of the independent variables in my data other than the target, which are the variables are correctly significant effect, which are the variables are important for me for my analysis to predict my target variable, that many people will be in the confusion. They will select all the variables. The peoples will do first variable, they will select first variable, and they will add one more variable. Like that, the peoples will be in the confusion while selecting the variables. So to address this one, so in R programming or in statistical iteration theory, so we have some selection procedures, variable selection procedures. That procedures will help us to do the to select the variables which are important for our data analysis for to fit a regression model. Okay, here also we have a simple one line or a single line codes are available to directly we can access which are the variables are important for our model. Okay, that I will show you here. Variable selection procedures, very important. Okay, so whenever we have putting of regression model, so we don't know which are the variables are really contributing to estimate my target variable. Okay, so in such situation, you can go for the variable selection procedure, so that the variable selection procedure will clearly will give idea. So these are the variables are really important for you. You can go with that. Like that, it will clearly explain to us. Okay, let's go with variable selection procedure. Selection procedures. Okay, so if you want to go for variable selection procedure, there are three procedures are there. One is forward selection, and second one is backward elimination. If any statisticians here, they might have listened these words. So backward selection, and last one is stepwise regression. These are the three procedures are available in statistical literature to select the variables, important variables or significant variables to the model to estimate our target variable. Okay, what is this forward selection, sir, and what is this backward and stepwise regression? So forward selection is nothing but, so in the forward selection model, first let's go. Let's have a simple example like this here. So in forward selection, the model will fit with initially, so without considering any independent variable, that is beta naught plus epsilon. So the model in the first step is like algorithm procedure, flow chart. Okay. First, the model will fit without considering any independent variables, how the dependent variable will be act based on the intercept. Now, once we fit a regression model, this one, it will fit. We don't want to fit. Okay. This insert step. If once it fit a regression model, then it will verify whether it is significant or not. A general obviously will get a significant with only intercept. Now, the next procedure is that now we have independent variables are there, right? 10 independent variables in our data, right? In these 10 independent variables, it will identify which variable is highly significant, the correlation with our y. There are 10 x are there. In these 10 independent variables, which variable is having high correlation, high significant effect showing on our dependent variable, that variable will be considered first. For example, let us take x3. Third variable in our 10 variables is having high correlation, high significant effect showing on y. Then x3 will be added to our regression model. So let us say beta 3 x3. X3 plus epsilon. So now this is your regression model. Now it will test whether the model is complete model, not regression parameter, whether the complete regression model is significant or not. If the model is very significant, then go for next procedure. In the next procedure, again, so x3 is over. Now x1, x2, x4 to x10 are there. Now in these variables, which one is the second significant correlation? Already first one is over. Now with the remaining 9 variables, which variable is having high correlation with y? That will search. Then what, for example, let us say this time the x6 variable is very highly significant with the y. Then it will add to our model, that is b6 beta 6 into h6 plus epsilon. Now this is our model. Now this model significance will verify. If the model is showing significant, okay, go for the next procedure. Otherwise, let us say if once we add this b6 x6 variable to our model and the model is showing insignificant, complete model is insignificant, then it will not take this into, it will stop the procedure. Why it will not go for searching is nothing but the remaining 9 variables b x6 is second highly significant. Even though if I am adding this second significant variable to my model is insignificant means then no matter of adding all the remaining variables, right? Why? Because the remaining 9 in the 8 variables, so x is the biggest correlation showing effect on y. Even the biggest is not showing effect means the remaining values will not show effect, right? That's why the model will terminate here. Like this, forward selection will work. I hope you understand. So forward selection, initially it starts from the intercept, then it will add. So in the remaining independent variables, let us say 10 variables, independent variables. In these 10 variables, which one is highly significant correlation, then it will consider it into model. So it will check the model significance. Now, if the model is complete model is showing significance, then we'll go for next search. The remaining variables, which one is the highly correlated, that will consider into model. Once the variable is added to the model, if the model is showing significant, that is additional R-square value is improved, then automatically we'll go for next search. Next search again will add it. Once it keep on will do, and where the addition new variable is adding to the model and it is showing invalid of the entire model, then that variable will be omitted. Still remaining existing model will be taken. Now see here, we got the optimal model. Let us say some randomly I have taken y equal to beta 1 plus beta 3 x3 plus epsilon. This is my random model. Okay. Now same situation coming to the backward selection. Backward selection is nothing but it is opposite to forward selection. First, the model will fit with all the variables. That is y equal to so beta naught plus beta 1 x1 plus beta 2 x2 plus and so on. How many values are there? We have around 10 values are there, right? So beta 10 x10 plus epsilon. So this is my model. Now in this model, so the first step is nothing but in these variables, which variable is least significant with y, that will be eliminated first, then we'll check the model significance. If the model is showing significance, model will show insignificance generally. Why? Because you have added all the variables, right? So definitely it will be show the insignificance. Now, so remain 9 variables will be there. Among these 9 variables, which one is highly insignificant? That will be removed. Then we'll see the remaining variable. Let it keep on, it is opposite direction. It will keep on removing one by one, one by one. So once it will keep on, if I removing, where the model shows the significance. For example, I have removed 5 variables and the remaining 5 variables are there. If I check the model significance, the model is showing very significant, then stop the processor. It's simply opposite to forward selection. Forward selection is nothing but one variable we are adding and testing the significance of the entire model. Here, backward elimination, same. So here it will identify the highly insignificant value first. That will be omitted. Then the remaining values model will check. So if the model is showing insignificant, again go for the elimination of one more variable which is highly significant. Second highly insignificant, sorry. Second highly insignificant. That value will be eliminated. Then again test for the model accuracy or model adequacy. If the model is showing insignificant, again go for the elimination. Again go for the elimination. So like that, if you keep on do eliminating, the where the remaining variables set will show the significant, then that model will be the optimal model, final model for us. This is backward elimination. Now going to the stepwise regression. So stepwise regression is nothing but it is a combination of forward and backward. It is one of the best we can call. Why? Because it takes a combination of both forward and backward eliminations. In this stepwise regression, initially the procedure will start from the forward selection, which means that first it will take the intercept model. Now in this intercept model, so it will take the next in the 10 variables, it will take which variable is highly significant to the model, that will be considered. Let us say previously we did first x3 we added, right? Now see, for example, let us say y equal to, so we done initial step plus some x3 will be highly significant, so I have added to the model. Okay, this is my first s model is significant. Now I'm going for searching for another variable. This time I got b6, let us say x6. So x6 will be the significant second significant correlation, so I have added the model is showing significant. Now again I'm going for searching for a new variable, that is let us say this time x4 is showing significance. Then I'm adding this model x4 and b4, beta 4 plus epsilon. Now see here, here, before x4 you have added. Why? Because this is the third significance correlation showing effect on y. So in case, because of adding this x4, if there may be a change in x6 or x3, earlier in the forward selection, we are not focused on these independent variables. We are focusing on only dependent variable and enter regression model, the regression model is significant or not. But in stepwise regression, if we add this x4 to the model, in case x3 or x6 got affected and showing insignificant, then remove that variable. See, for example, here I'm adding x4, right? If I were adding the x4, maybe x6, b6, the regression parameter b6 shows insignificant, then eliminate this one, keep only x3, b4. It is eliminated. Next, again in the remaining variables, it will search. Let us say this time x5 will be the significant variable I got. That is b5 x5 plus epsilon. Now, if I add this x5 to the model, maybe x4 or x3, anyone is showing insignificant or got affected, eliminate those. Otherwise, because if you add x5, there is no any effect on x3, x4, keep. Next, I'm going for one more search. If the model is significant, complete model. Next, if the model is significant, again, I'm going for search. This time, let us say X7 we got. Second significant, fourth one significant correlation. Now, if I add this X7 variable randomly, so maybe let us say X3 got insignificant. That beta 3 parameter got significant, then eliminate this one and go the model is between this one. If the model is significant, again going for search. Like that, so we have to take the new variable from the data, we have to add into inside model. If there is no any effect of independent variables itself and only showing effect on y, then keep. Otherwise, if the independent variables are affected and it becomes invalid, remove that. So like that, keep on, we are adding, removing, adding, removing, adding, removing. Finally, we'll get a perfect optimal model. That is the best model for us to climb into the any investigators. I hope you understand what is stepwise regression. So forward selection is one direction, forward one is selecting. Backward elimination, we are eliminating one by one values, which is insignificant. Stepwise is thing, both forward, it is a combination of forward and backward eliminations. So this much procedure is there. Okay, fine. So actually we have one chapter, complete one chapter. This one, it's a variable selection procedure. We have to draw flow charts and all. Okay, I just simply I have conveyed to you people. I hope you understand. Okay, fine. Now how to perform these techniques in our R programming language? So easily we can perform. So if you want to perform this variable selection procedures, a required package, that is OLS or is a package required. Okay, now I'm going to install this package. So in packages, install OLS or see this one, OLS RR. Okay, take cap small letters, don't get a caps. Okay, OLS RR, ordinary list squares. Okay, install this one. Yeah, it is installing. It is a little big package, that's why it is taking time. Here we can see the option stop button, it's continuously working. Yeah, yeah, successfully unpacked. Oh, fine. Here we'll search whether it is installed or not. It is installed. See, OLS RR is there. Tools for building OLS regression models. Yeah, we want this only. Yeah, I have loaded into my console, that is library of OLS RR. Next, if you want to perform forward selection, that is OLS, you just write OLS. If you enter this OLS itself, automatically you will get a lot of options. Okay, in this option, you can see the word forward option, OLS, Molos, plot, mm, plot. Where is the OLS forward? That's one. We'll write OLS forward. Is there? OLS step forward. You can see here OLS step forward AIC. AIC information is nothing but Akaika information criteria. It is an information criteria. So information, I said no. Model is significant. Model is insignificant. Always I pronounce this one. Model significant. Model insignificant. Variable significant. Variable insignificant. How we will check the significance or insignificance? That earlier we are going with p value, no? If the p value is less than 0.05, I'm saying significant, otherwise not significant. That is, instead of p value, you can go for AIS, Akaika information criteria. It is an information criteria. It is like a one cutoff value. So this Akaika is the author name who invented this information criteria. Akaika information, based on Akaika information criteria, AIC values, we can say that the model is significant or insignificant. Or we can go with p value. Based on the p values, you are going for selection the variables, either the significant or insignificant. R2, that is R square value. And SBC, okay, stepwise, SBC is nothing but Shivaj based information criteria. Okay, SBH, Shivaj based information criteria. Okay, like this, we have AIC, BIC, Bayesian information criteria. Like that, there are many information criteria are there. Among these, just to simply go with P. Why? Because this is the only I thought to you people. So if the P value is less than 0.05, significant, otherwise not significant, I say no. The same thing, go with the OLS step forward under the criteria is P value criteria. Easily we can understand. Okay, and we don't want to worry about that. You can go with any information criteria, either AAC, BAC, or SBIC, no issues. But when we people we have some idea about p value, no? So we just simply go with p value. Okay, just p. Okay, now in the OLS underscore step underscore forward underscore p. So I'm going to perform forward selection procedure based on the criteria p value. So inside the parenthesis, give your model. What is our model? ML, right? So you have to fit the data. So the data is with all the variables. Okay, regression model, you need to fit with all the variables. Okay, that is the regression model. Here I fit it. That is MLR. Okay, that's I'm copying here. MLR. ML, just give this one and run it. Yeah, it's a beautiful output, like a table format we got. Easily we can understand. See here. See, this is the big output we got, but very nice. See, OLS step forward, stepwise summary. One summary table it is giving. So step 0, 1, first step 0. First step is base model without having any intercept. So this is the Akaika information value, AAC value, and Shiva's Bayesian information value SBC and SBIC R square value. But initially R square is very zero, adjust R square is also zero. Now, in the data, so weight will be the first significant variable, which is highly showing effect on MPG. We know, right? Mileage, it depends on the weight of the cars. That's why the first variable is entered into the model. In the first step. Okay, AAC information is downwards. Generally, when the AAC is low or BAC, if the low AAC, low BAC values will be the best one. Okay, see from 208 it is decreased to 166. So there is a formula, sir. AAC, BAC, SBC, all the formulas are there. So I'm not going to discuss with you. Just I will go with R square value. Why? Because we know how much R square is the accuracy. Okay. So SBC is downward, SBIC is also downward. Go here. 0.75. 75%, or you can take adjust R square value 74. So 74% of variation in MPG you can explain by taking only single value, single variable weight. If you take only one variable into your model, you will get 74% accuracy. At the same time, next search in the second step, cylinder is taking. But we never consider cylinder in our model. Earlier we performed yesterday and we performed right simple irrigation model. Just we assumed that so the mileage will be affected by the weight and horsepower. But the number of cylinders in the car that is also showing effect on your mileage. That see it is revealed. The information is extracted where. So till now I also don't have much information on these cylinders. See now by seeing this data, cylinder see the number of cylinders is variable, right? The number of cylinders in the car. So if you have more number of cylinders, that is also there will be effect of your mileage. So the second is cylinder is selected, and these other values are downward. And here we can see adjust R squared 81. So if you take the cylinder, 81% of accuracy you can consider both with the weight and cylinder. It is not a single value, so it is a combination. It is a cumulative one. So 0 plus 7, 0.7774 plus the remaining cylinder percentage. If I if I take these two values, weight and cylinder into model, then I get the 0.81. Next, one more is adding horsepower. So finally, with these three variables, if you consider into model, you will get 82% accuracy. Here, one thing also we can do. So does not require to consider HP variable into model. Why? Because see already with these two variables we got 81%. No, so may not be required to get 1% of accuracy to increase 1% of accuracy. There may not be reasonable to consider this horsepower variable into model. Why? Because the model will be very big. No, three variables will be there, three parameters, again testing of parameters and testing of complete model. It's a huge time, it takes time. Okay, so for getting only 1% of accuracy, this may not be required to consider according to my situation, my knowledge. But if sir no sir, that 1% is also valid. Whenever we are going with medical data analysis, no, there is very important in the medical information, in the medical data analysis, medical industry. So one person is also plays a vital role. So that affect a lot of patients. A single person, 1% or 0%, 5%, like that. If you are ignoring that small percentage of no, automate that will show a lot, huge effect on the patients. Okay, in the situations we can consider. Here also, if you want, you can consider. The model is showing if you consider these variables into model, that is weight, cylinder, horsepower, you will get 82%. No, sir. Already I got 81% with these two variables. I will ignore this third variable into my model. Means you can ignore, no issues. So finally, so these three variables are selected with the procedure of forward. So 82% accuracy we got. So this is the final model output. R value, next R square value, square of the correlation coefficient, adjusted R square value, pre at R square value, predicted R square value. This one. Next, mean absolute error, root mean square error, coefficient of variation, AAC, SBC, also they have given pronunciations also here. Shiva's Bayesian criteria, SBCs. Okay, these are the models. I mean, accuracy of the model adequacy values. You can take anyone. Root mean square, you can take mean square error, you can take coefficient of variation. Okay, generally you go with simply R square value. That is very easy to interpret. Okay, why? Because again you are taking mean square error. Then mean square error again you have to compare with another model. So which model is having less mean square error? Then you have to say again this model is very best. So here we are not going for comparison purpose. No, just I'm checking whether my model is good or not. how much accuracy my model is having. Simply, I will go with adjusted R square value, that is 82%. And this is the ANOVA table, analysis of variance. This I will show you in the next after this completion of this topic. Okay, analysis of variance, we know it, ANOVA. Okay, this is ANOVA table. Okay, sum of squares will be there, degrees of freedom, mean sum of squares, and F test. So why we are performing ANOVA here is nothing but to check the model significance. Now here I have taken here the model is fitted with these three variables, no, weight, cylinder, and horsepower. Now we have to say that if you consider these three variables, you got accuracy is 82. Whether your model is significant model or significant enough to explain about MPG or not, then we have to go with ANOVA. To test the significance of entire model, we are going with ANOVA useful. So here we can see this last significance value 0.00. Significance value is nothing but p value. Okay, if the p value is less than 0.05, it's absolutely we can say the model is significant. Yeah, here we got the p value is zero, complete zero. So we can say that the fitted regression model is best one, significant one. Okay, and finally parameter estimates. So what is the parameter values? So intercept value, weight, cylinder, horsepower, standard error, and standard beta, and t-test statistics value, significance values. The parameter significance values, what is the lower upper confidence limits. So this is the big output we got. This much output you will get. CFC, weight, cylinder, horsepower is there, no? Sir, I want to see the full details about this procedure, how it is iterating. That is also you can see. Here we have code, no? OLS, step, forward, within the bracket MLR, no? Here, keep comma, details. You add just one argument, details equal to true. Just a minute. If you just add details equal to true, just one argument, you will get full description about your full complete step-by-step procedure you will get. Run it. Yeah. See, forward selection is working. Yeah. Go over. See full output. Here you see. So I have given full details. I want to know how step by step my forward selection is working. See, first candidate terms. Candidate terms are nothing but independent variables in our model. So these are the 10 variables other than MPG. MPG is target variable. Okay. Next step 0. Model is considered MPG tilde 1. Tilde 1 is nothing but only intercept. There is no any independent variables. Now R square is 0. Iterating, initiating stepwise selection. Now selection procedure is initiated. Now see, based on some t values and then R square value, adjust R square value, AAC values. Among all this one, so it is going to be select the weight. Why? Because weight is having less AAC. Here you can see this 166 less AAC and accuracy is 0.74. So for all the variables, so among all the variables, weight is showing significance, more significance. That is 0.7 for accuracy will get if you add this weight. Now it is taking 0.7 for first. Otherwise, see the p values. Which p value is having more significant? 0.00. So these are all 0.00. Here is showing only 5 decimals. But if you take keep on many decimals, among all the decimals, so weight will be highly significant. It is close to 0. That's why it is having highest significance, that is 0.74. Now this first variable is added to the model. Here in the C. Step 1, selected weight. So model is now MPG tilde weight. So only one independent variable estimating one dependent variable will get the accuracy is 0.75. Next, again going for second selection matrix table. See, either you can go with p value or R square value or adjust R square value or AAC. So let's go with this time p value. See, among all the p values, cylinder is having less p value, close to 0, highly significant. So you will get 83% accuracy if I add this to my model. Yes, so cylinder is selected. Now weight plus cylinder, we got 83% accuracy. Next, selection matrix, again it is going. So among here higher HP is having, initially it will be arranged in ascending order. Okay, HP is added. So HP is 0.14. Here you can see this. HP is showing insignificant. Why? Because p value is not less than 0.05, but we have accuracy is 84. Here we have 83. one parameter, it is showing that okay, both are considerable nearer only, you can consider into a model. So just it is considered into a model that weight, cylinder and horsepower. Finally we got 84%. Next selection matrix, again it is going. If I go here again, here see the p value is going to be more than 0.05 and close to one side. Okay, and you can see this accuracy r square value 0.84 only. Here already 84 is there. Again 84 means does not require. Model will show insignificance. Just stop the procedure here. Then no more variables to be added. Variables selected are weight, cylinder, horsepower. This is the things already we saw. That is stepwise summary, model summary, ANOVA and parameter estimates. So we'll get only these three tables finally out final model. So we cannot see this what is happened prior if you are not mentioning details equal to true. But if you mention details equal to true, full information we can see. Okay. Next, just similarly we perform OLS forward step forward selection. Okay, sorry, backward elimination. OLS underscore step backward P. Okay, same MLR. Run this one. What are the variables are selected this time using your OLS backward elimination. So stepwise regression, backward elimination. So variables full model, cylinder, VS, car, gear, and drat are removed. And what is the final model we got? See, these are the variables are removed. Okay, final model. Okay, stepwise summary. So finally, we got accuracy is 0.86. This R square value we can see 83. But compared to forward and backward eliminations, forward selection is giving better accuracy 0.84, but here 0.83. So we can go with forward selection. Okay, any selection procedure you can follow. So which gives more accuracy. That is generally we will consider right. Why? Because we need to show more accuracy. So is here, and what are the variables are selected? Here displacement, horsepower, weight, cubic, and AM. So 1, 2, 3, 4, 5. 5 variables are considered into model backward elimination. So these are the variables are removed. These 5 variables are removed, and remaining 5 variables it is keeping to show the model is significant. That is with accuracies 0.83. Okay, going with backward elimination, it is better to go with forward selection. Why? Because we are getting very less number of variables and we are getting more accuracy. Generally, we need that only, right? We need to select a very less number of variables into model, but we need more accuracy. So it's like optimization. Okay, less investment, more profit. Okay, that's what we need. Okay, okay. So let's step backward. We'll do this one also. Then we'll understand which one is good. Okay, OLS step all possibles. Okay, this is nothing but all possibles are step both. Step both. 1 minute MLR. Just 1 minute. I will test. Okay, fine. This is only code. OLS step both. Both is nothing but both forward and backward combination. That is stepwise regression. Okay, it is a combination of both. It's performing. Now we can see this one. You can, I think, you can consider this one. Stepwise regression. Why? Because it is combination of both and giving better model. See, only 2 variables, weight and cylinder is selected. Once we select only 2 variables, how much accuracy we are getting? 81. This is fine, right? Yesterday in the first forward selection we saw 83% just if we add one more variable, that is horsepower. For getting 1% increment of accuracy, so we are adding horsepower. So that may not be required, right? So this is the best option for us. See, finally we got, so OLS step both multiple integration model, only 2 more variables are added. There is no further variables are removed or added. So plus is nothing but added. There is no any subtraction of the variables. Okay, just these 2 variables is fine to explain your mileage. That is weight and cylinder. No, it does not require horsepower also. So with these 2 variables, you are getting 81% of accuracy about your regression model. That is fine. And this is ANOVA model. Our p-value is also significant. So easily we can say that there is a highly significant effect of our regression model. And finally, these are the parameter values. So with this, we can final optimal model. Let's go with optimal model. Optimal model. So what is optimal model? MPG, miles per gallon, which is equal to, so 39.686. Here you can see this one. This one. So 686 minus 3.191, which is multiplied by weight, and minus 1.508, which is multiplied by cylinder. So this is the best model, final model. So this model will give 81% accuracy. 81% of accuracy. So 81% of variation in MPG can be explained by weight and cylinder. So now you give the weight and cylinder values here, so you will get mileage easily. Okay, just now we'll fit a new regression model. So new regression model, this new MLR, new regression model, multiple linear regression model, that is linear model LM of what are the variables we'll take. MPG is our target, tilde, so weight plus cylinder, only two variables is fine. Now data equal to empty cards. Now run this one, take the summary of NLMR. So sorry, NMLR, new multiple regression model. If I run this one, so we got 81% of accuracy. So this is the final model for us to show the to show about the best fit of the model. Okay, I hope you understand. So like this, we have to select the variables. So even if we don't know about the idea about what are the variables and whether these variables are showing effect on MPG or not, or whether the variables are showing effect on your target variable or not. So if you don't know any information also, just take just decide your target variable and dump all your data variables into model. Okay, then go for checking. So you can go for OLS forward selection or backward elimination or stepwise. Among these three techniques, which technique will give more accuracy and having less number of observations, less number of variables, then go with the technique. Okay, by claiming that, so this is a technique I have used to select the variables, then fit a final regression model to show the accuracy. So with these variables, we can, with this model, we can go for further prediction. Understand? For example, I will do prediction also here. Okay, how to do prediction? Now this is the final model we got at NML. So if you want to predict a new value, let us say predict what we are going to predict. So I want to predict NLMR, new regression model, NMLR. So with the data dot frame of what are the values we have? Let us say uh, weight equal, let us say 2 tons I have will give, comma, and cylinder equal to, let us say 6 car cylinders I will give. NMLR not found. Oh, sorry, type of mistake. NMLR. See this one. What I did is nothing but just I predicted the future values. So what the model I have here, NMLR, the same model I have taken here. Next, I have taken one object data.frame. Why? Because here two variables are there. No, I want to give two values. So instead of giving C of two values, just we have to define in a prediction like using data.frame. Okay. We know, right? In the first class, I discussed about data.frame to represent the data in a tabular form. Here, weight, cylinder, and then MPG, three variables are in the tabular format only, right? So just we have to give the same notation wise. That is data.frame weight W2. I have given. Let us say I have a new car that I purchased the car. The weight is 2 tons. I have mentioned 2. Next, number of cylinders of my car is 6. Now with this with this information, I want to estimate my mileage, MPG, predict option. Okay. Now if I run this one, I got, sorry, I select this one and run it. I got 24.25, which means that there is a 24 miles per gallon my car. So which is having 2 tons of weight and 6 cylinders car. So like this we get predict. Okay. Any doubts are here? Stopping here and then I'm going for testing procedures. If you have any doubts, you can ask here. Quickly, we'll finish this regression. Actually, this much concept yesterday itself I have to finish, but due to time constraints, I didn't. Any doubts if you have? No doubts, then I will jump into my testing concept. Only one comment, that is good afternoon. Yes, good afternoon, sir. Yeah, fine. Hmm. We'll go with our R code again. Yeah, fine. So here I'm stopping here. Then I'm going for a testing part, testing of hypothesis. Ah, a new concept I'm going to start. Yeah, this I will clear. So you can click this option, brush option, which means that it will clear all our R console. Yes, R console is very new and just I'm closing this one. It is unconfirmed. You want to watch it? Yes, I don't want to clean all my environment. Just I have cleaned. Now my environment is free. There is no any flaws, and the code is also either I can take new, otherwise day 5 right. So I will work in the same R script so that you can easily can access what I thought every day wise. Okay, fine. Now testing of hypothesis. So first, let me discuss about the hypothesis and what are the types of hypothesis and why do you want to use this hypothesis and why do you want to test? Generally, hypothesis is nothing but it is a statement about the population. Okay, so why this concept actually counts is nothing but so generally this concept comes from the sampling. Okay, so for example, whenever we have a population and when we are unable to see the population, then we will also sustain. Whether this information is true or not, also the otherwise, temporary solution to a problem is hypothesis, sir. It's not a temporary, sir. Okay, and I have fine. We'll go with this. Yeah. See, testing a hypothesis, it's two types will be there. One is null hypothesis, another one is alternate hypothesis. So null hypothesis, the people's way should be positive, or simply we have to think that it should be a neutral statement. So we have to give, for example, let us say one example. I said no, one example for paid t-test. Okay, let us take you drug A is existing one, and drug B is newly invented one. Now, if you newly innovate this drug A and drug B, both will perform to test which drug is superior or which drug is inferior than other one. Okay, in such situation, our null hypothesis should be neutral. Both the drugs are performing equally. There is no any significance difference between both the effect of both the groups. Like that, we have to give some neutral statement, that is equal statement. So in null hypothesis, always it will be the equal statement, that is neutral statements. For example, let us say I have a population. From the population, I have taken some sample. Now, I will say that the sample characteristics will be equal to population characteristics. That is my null hypothesis. It's a neutral statement. Neutrally, I'm saying that. So, what the sample I have taken, the sample should be equal to population. Next alternative will be it is opposite. The sample characteristics are not equal to population characteristics. Okay, this is the way we have defined our null hypothesis and alternate hypothesis in our statistics. Okay, so now for example, let us take we'll discuss some statistical tests. Yesterday I said it. If you want to find the difference, okay, we'll use t-test, ANOVA. So one sample t-test, two sample t-test. Like that, we will use some many statistical tests, right? That's this we will use today. We'll learn here how to perform. Okay. First, we'll go with a single sample, one sample t-test. So it's showing right. Yeah, now it's okay. Actually, I'm not getting this tab. That's why I got confused whether you're listening or not. Okay, fine. Now it's okay. See, first I will go with the one sample t-test. That is single sample t-test. Single sample t-test. What is this single sample t-test? Is nothing but type of mistake. Single sample t-test. Single sample t-test is nothing but so here we have a population, and for example, if you don't know, if you have some information about the population, but we are unable to read the entire population, then we are going with the single sample observation. Now let us take one sample group I have taken sample observations. So from these sample observations, I want to compare whether the sample characteristics, for example, let us mean. So whether the sample mean will be equal to the population mean or not, then we are going with comparison purpose with use by using one sample t-test. As I have given introduction about this, right? One sample t-test. The same that we will perform here. Okay. So if you want to test whether the sample mean is equal to population mean or not, so we will define with the null hypothesis. So null hypothesis we are indicating with H naught. Okay. So in statistics we are indicating null hypothesis H naught. So my H naught is that there is no significance. There is no significance significance difference between sample mean and population mean. That is H naught is so sample mean. Let us take x bar equal to population mean mu. Okay, other mu equal to x bar. Okay, like that we can do a sample mean. Let us take I will give mean of sample will be equal to mean of population. Just I have taken one characteristics that is called the mean. Okay. Now I want to test whether my statement is true or not. So what is the alternative for this one? H1 we will denote with alternate technique, alternate hypothesis. It is not equal. Okay. Let us take not equal. Here one more thing concept will rise. One tail or two tail. So one tail and two tail is nothing but here we are saying the statement is not equal, right? Not equal is two tail test. Both sides we are testing. Okay. Our one tail test is there. For example, let us say sample mean is less than the population mean, or population mean is greater than the sample mean. So like that, any one side, either left side or right side. That also we have to consider that one. So as of now, basically I will go with the two tail test. Okay. So sample mean is equal here, null hypothesis, in alternate hypothesis, sample mean is not equal. Okay. Now if I want to test this statement, okay, first we'll take up one population. From the population, we'll draw one sample observation. Now we will check whether the sample mean is equal to population mean or not. Okay. Instead of going to generation, we'll go for generation of data. Okay. I will generate data, and then from the data, I will take some sample observation. Then I will go for testing. Okay. So whenever we are going with this parametric test, I said right, we have to take some assumptions. Generally, if you want to perform t-test, so simply we have to assume the data should be normally distributed. Okay. So for that, I will generate the data from normal distribution only. Okay. So data, let us take population data, POP, which is equal to. So if you want to generate data from normal distribution, so we need to know what are the parameters of normal distribution. So the parameters of normal distributions are mean and variance. That is called mu and sigma square. So we have to take some arbitrary values for these parameters. Then using the parameters, you can generate number of sample observations. Okay. So the code is that R norm, random numbers from normal distribution, or norm is nothing but normal distribution, or is random numbers generating. Okay, so how many numbers? First we have to indicate how many numbers you want to define. For example, let us say I have to draw 1,000 observations. I have to generate 1,000 observations. Okay, so first we have to give sample size. Next, mean value we have to give. Let us say on an average the mean value for my data should be 30. Okay, and let us take the standard deviation. Okay, variance, right? So we have to define a standard deviation value. Let us say the deviation of the observation should be 0.5. So here three arguments. One is the sample size. So how many observations you are there are you are going to generate? Okay, there are 1,000 sample observations I am going to generate. Next, 30 will be the what is the average value of your data. So for these 1,000 observations, 30 will be the average value approximately. Okay, next 0.5 is the deviation. So how much the data points are deviated from the mean. Okay, 0.5. Simply I have taken a small number. Okay, now if I run this one. Next, you take this one, POP. Now, if I run this POP, you will get 1,000 observations. See, 1,000 observations have been generated. Almost all the observations are nearer to 30. Why? Because the deviation is 0.5 only, right? Very less deviation I have given. If you want, go with this histogram, hist of POP. So run it. See, the histogram is showing almost exactly normal distribution. Why? Because we have generated data from normal distribution only, right? Obviously, data will be normally distributed. Okay, more observations are near to the mean, less observations follow the tail ends, left and right tail ends. Okay, so okay, fine. Yes. Now, from this population, let us say I will draw one sample groups. Yes, one. Okay, so let us take the sample. This time I will draw. So in this S1, I have created one object. So first sample groups I'm taking. Okay, let us take sample of. So if you want to draw sample observations, go for sample code. Okay, sample of. So how many observations? For example, let us say you want to draw from this 1,000. Let us say a small 10% will draw. That is 100 observations I will draw. Okay. So from the sorry. First we have to define data, right? From where we have done. So population. So from the population, we are going to select 100 observations. Randomly, I'm drawing some observations from the population. Okay. So code is sample of the population, POP. So from this 1,000 observations of the population, just go for randomly, simple random sampling. I'm not going for systematic. I'm not going for certified. The simple random sampling I'm performing with the code is sample of population and 100 observations I'm going to select. Okay, just if I run this one, yeah, now we run here. Yes, one. These are the sample 100 observations which are taken from the population. Now, for example, let us take, I want to test whether the sample mean is equal to population mean or not. This population mean is 30 already we know. Okay, just I want to test whether the sample mean is equal to population mean or not. So then we are going with, so one sample t, there is a single sample t test. When you know information about the population. Okay, based on your sample, whether you want to test whether the sample mean is equal to population mean, then we are going with t-test, one sample t-test. So code is t dot test. Very simple, just one line, single comment, t dot test, t-test. So within the bracket, so what is the data we have generated, drawn? Yes, one is sample data. So which is comma, what is the mu? Mu is nothing but mean, population mean. What the population mean we have taken? 30, right? Here we have the random taken. So just give the 30. Otherwise, you can calculate from the population data. Okay. Just already I have given the arbitrary value 30. So mostly the 1,000 observations will have mean is 30. Okay. I'm not going to recalculate again. Approximately will be 30 only. So I'm taking mu equal to 30. Now what is the t-test is performing here? I'm going to compare the sample mean with the population mean by taking the all observations. Okay. Don't directly compare. Just find the mean of sample one and what is the mean of the population sample. Both the means are equal. Then don't claim that the sample mean is equal to population mean. Many people will ask us question here, sir, why we want to take a sample? Already we know population mean and sample observations are there. I will calculate the mean of the sample observations. Now both the means I will compare. If means are equal, then I can claim that so both are equal. Why do I want to test? Why? Because so the means is comparison is nothing but is not only the comparison of means, there is a hidden variation in there. That variation also we have to compare about the data. Okay, simple example I will give to you people. So why do we want to why should not go for a comparison of only mean without the considering variation? Let us say if I take some observation, let us say I will take a small observations, 49, 50, and let us say I will take like this 49, 50, and 51. Simple values I will take. So what about the mean will get? So mean will be 50, right? Okay. Now let us go with, I will give one more data, 40. Let us go with 45, 46, 47, 48, 49, 50, 51, 52, and 53, 54, 50. Just I have taken one sequence numbers. Now what is the mean of this data? Mean is 50, right? See, this data is having three observations. Mean is 50. And this observations is having mean is 50. Now, will you say that these two data observations are same? Why? Because means are same, no? So this should not be claimed. Why? Because the data variation also we have to consider inside. Here only variation will be, I means I have taken a sample data, simple example. So just by difference is 1, 1. So maybe there is different values will be there, but the mean will be same. So data points are very far, but the mean is comes the same. Both the sides, the mean is come without considering the variation. So comparison should not do. Okay, I hope you understand why we are not testing, why we are not only comparing the means of the two data sets. Okay, don't do this one. So t-test will consider the inside variation, then we'll compare the means, both whether the approximate means, both the sample mean or population mean or two group means are equal or not, it will test. Okay. Now we test run this one, t dot test. Yeah. So we got the output, one sample t-test. So t-test statistics value, this is minus 0.02. So while comparison with the table value, t-table value, so ignore this minus. Why? Because modulus t we have to compare with the table value and degrees of freedom. The number of observations having the freedom to vary within the data. That is called degrees of freedom. Okay, 99. Which why? Because t-test degrees of freedom is n minus 1. N is nothing but 1000 observations, sorry, 100 observations, sample size. So n minus 1 is 99 observations you will get and go with the p-value. We don't want to consider this test statistic value or degrees of freedom. Directly we can go with the p-value. What is the p-value it is showing us? The p-value is above 0.05, which is mean that the p-value is going to close to 1, insignificant, showing accepting the null hypothesis. What the null hypothesis we have defined here? The null hypothesis is that sample mean is equal to population mean. They have mentioned alternate hypothesis also. See, alternate hypothesis. What is the alternate hypothesis they have mentioned? True mean is not equal to 30. True mean is not equal to 30 means nothing but this one only, right? What we have defined x1, not equal. So sample mean is not equal to population mean. So what we have given population mean is 30. The true mean is not equal to 30. So this is alternate hypothesis. Opposite is alternate population. True mean is equal to 30. That is sample mean is equal to population. That is null hypothesis. So they mentioned alternate hypothesis. Clearly, if you are not unable to define null hypothesis and alternate hypothesis, then take the help of the R command itself. Then the output is showing alternate hypothesis that true mean is not equal to 30. So then null hypothesis should be true mean is equal to 30. I mean sample mean is equal to population mean. So now the p-value is greater than 0.05. We are going to accept the null hypothesis. There is no significant evidence that to claim so sample mean is not equal to population mean. So we are going with null hypothesis. So we did not get any evidence to reject the null hypothesis. Okay, to reject our positive statement. Okay. Next, this will be the 95% confidence intervals for our mean. Okay. So mean will be 29.99888. This is the mean of sample. What we have taken S1, the mean of the sample is 29.98, which is almost approximately equal to 30. By taking the variation in also consideration to data points. Okay. So this is one sample t-test. Now, similarly, I am going to compare two sample t-tests. Now, forget about the population. I don't have any information about the population. Just I know observations, and I have taken sample of some observations from the population. Now, I want to compare whether the drawn two sample observations will be equal or not. So, based on their means, then we have to go. We are going with two sample t-test. Okay. Let me draw one more sample. Let us say S2 sample of same population. Again, I will draw 100 observations. This time you can draw any number of observations also. There is no rule that should be equal. Okay. Let us say this time also again I have drawn 100 observations. Now I want to test whether this second sample mean is equal to population mean or not. Okay. So this is some more 100 observations. Don't think the same observations you will draw. Sample, right? So different number of observations will taken from the population. Same sample may not be possible here. Okay. Now, so again, I'm performing two sample t. This same code t dot test. So within the bracket, what are the observations? One is S1, second one is S2. So S1, S2, two sample groups. Now compare these two sample groups and test whether these two sample means are equal or not. Now, what is the null hypothesis here in this situation? We are again saying that there is no significance difference between sample one group mean to other population. Second sample mean group two. That is, sample mean is equal. First sample mean is equal to second sample mean. Alternate hypothesis: sample means are not equal. Okay, that's will perform here. Yeah. So we got alternate hypothesis. True difference in means is not equal to zero. What is this meaning? True difference in means is not equal to zero, which means that there is some difference exist. Then what about this null hypothesis? There is no difference. Okay, opposite to this one. Now our statement is no difference. So here difference. So no difference is nothing but sample two sample group means are equal. Now we'll see whether it is good, true or not. So what is the p-value we got? The p-value we got 0.71. Okay, so it is also greater than 0.05. We can claim that. So sample mean is equal to population mean. Sorry, sample first sample mean is equal to second sample mean. We are going with null hypothesis, accepting the null hypothesis, and there is no any evidence we got to reject the null hypothesis. Okay, and this is the first sample mean 29, and this will be the second sample mean 30. So approximately these two sample means are equal. So this is the way we can perform our one sample t-test and two sample t-test. For example, if you have a paid data, so that is, I said no, pair of observations. So I gave one example also, before and after. So it's the same patient, and I want to test whether whether if I invent any new drug, and I want to test whether this new drug is showing effect on the patients or not. So first I will take a before giving the drug, what is the measurements, and after giving the drug, what are the measurements. Let us say BP only if I consider. So what is the BP before giving drug and after giving drug? These are the pair observations. Go for the comparison of these two pair groups. Then again we can use t-test. So additionally, you have to add like this, comma paid equal to true. So if you add this argument, that is called paid test. If you mention true, so these two groups will be considered as it depends on each other. So it will perform paid test. If you are not giving anything argument here, then it's considered as a completely independent. By default, it will follow independent to sample t-test. Okay, as of now, these two groups are independent, right? So we should not consider paid equal to true. However, let's go with for just for our explanation purpose only, right? Just we'll clarify. Yes. So same null hypothesis. Why? Because true difference exists or not. So null hypothesis no not exist. Alternate hypothesis exist difference. So again same comparison p-value. So page it is test is also showing that there is a there is no significance evidence to reject the null hypothesis that both the groups are having same mean. So like this we can perform our t-test. So what is one sample t-test and two sample t-test, and last one is paid t-test. Okay, this is the way of performing t-test. And the next one is, for example, here if you draw more than two samples, I had drawn only sample 1, sample 2. Let us say I will draw one more sample. Let us say S3. Sample of population, comma, 100. Let us say I will draw some more 100 observations. Let us say this time I will draw 50 observations. Simply, I will draw 50 observations. Now, I want to compare whether these three group means are equal or not. Now, how many groups we got? Three groups we got, right? Now, I want to compare whether these three groups are equal or not. Okay. So, to compare more than two groups, so t-test will not be suitable. We have to go for ANOVA, analysis of variance. Now, ANOVA will come into the picture. Okay, so whenever you want to compare more than two groups, then two group means then we are going with ANOVA. A simple ANOVA code is AOV. So, but if you want to perform this ANOVA, we have to arrange the data first. I will arrange the data simply. I will show you. Why? Because three groups are different, no? S1, S2, S3. So these three groups we have to arrange in one sequence. First observations, next second sample group observation, and third sample of the group observations. So we have to keep on, we have arrange. So see here how I will arrange. So let us take, we'll arrange. First one is 100 observations, second one is 100 observations, and third one is 50 observations. Let's go with like this. For example, let us take, I will create a one data dot frame. So data dot frame. In this data dot frame, I'm making one table data. So first will be let us say C of concatenation I'm doing S1, comma, S2, comma, S3. What is the meaning of S1, S2, S3? S1 is having 100 observations. Next, concatenating the another 100 observations. S2, next concatenating other observation 50. That is S1, S2. All are comes in one line. That is first 100 will come, next 100, next 50. Totally will get 250 observations in one set. So this will be one set. Let us say this will be uh, data. Now data, right? Let us say sample equal to, so C of S1, S2, S3. Let us take CR also. Let us say observations, right? Let us say OBS, observations I will give. Okay, just I'm creating one table format data. First will be all observations what I have taken, that is S1, S2, S3. Okay, now in the second column I will create, let us take category. Okay, otherwise group, GRP, group. Okay, what is the group I'm giving? So group equal to CR. First will be 100 observations, right? First group. Let us take C. The first one here will be, let us take repeat, REP, repeat 100 times. This code is nothing but repeat one value 100 times. Just I will run this one, you will understand. See, 1 repeated 100 times. So that should be in place here. Next, after this one, next, again repeat second group, right? Let us take repeat 200 times. Next, third one, again repeat. How many times this is? Third group is 10, 50 times only, right? 50. Yeah. Now what I did, I have created two variables with this data dot frame. One variable is observations, OBS. Other variable is group. In the first variable, I want all the observations in all the groups, S1, S2, S3. Now in the second variable, group, I want category wise, 1, 2, 2, 2, 3, 3, 3. Why? Because to identify the category wise data. Okay. So just run it. Object S3 not found. Oh, we did not run this one. Let's go with the running of this one. Yeah, executed. Now S3 executed. Just simply will run this. And now see here. I have one data. So this is the data we have created. See, observations, OBS, first variable. So OBS and group 1, 1, 1, 1, 1, 1, up to how many values will be there? 100. Why? Because first 100 will be the first sample group. So sample one corresponding one. Next second 1 So we have again 100 observation, that is S2 sample observation into 2, 2, 2. So category is 2, 2, 2 and so on we have given. Next and so on. The third one is we have given. So from 201 to 250. Just I have arranged the data in a tabular format to indicate separate category wise. Now I will go for performance of ANOVA. So let me store this data into any one object. Let us take sample group. Let us say sample group is a one object I have taken, I have created, I have stored this data into sample group. Now take here ANOVA, AOV, of. So first we call independent variable. What is independent variable we have here? Independent variable is observations, right? Observations, OBS, right? Let us take sample group dollar. Here one data I have created. So that's why I'm using dollar. Otherwise, you can attach the data, attach sample group. Then directly you can access OBS and GRP direct variables. Okay. So OBS tilde, same like regression. Okay. Tilde. So again, sample groups. In this sample group, according to I want to go group wise GRP. Here, comparison is observations. I want to compare observations in the sample group. That observations has to compare according to their group wise categories. That's why I'm doing sample group dollar $GRP. So now I'm going to compare the sample groups observations according to their category wise group 1 1 1 2 2. Now from how this will execute is nothing but, so in this data group wise 1 1 2 2 3 3 will separate, and the corresponding observations, that one corresponding observations, two corresponding observations, three corresponding observations separate it will take, and it will compare the mean by taking the variation inside. Okay, that will come, run it. Yeah, this is we got. So this, instead of explaining this one, we'll go for a summary of this model. Why? Because ANOVA is always in the tabular format, right? We know we have source of variation, degrees of freedom, sum of squares, mean sum of squares, f value, f table value. Like that, we'll have a table, right? ANOVA table. That table, if you want to get from this output. So instead of this is also same only, but instead of expanding this one, many of us we read ANOVA in a tabular format, right? That I will draw. So let's me store this model output into any one of the, let us say ANOVA. Just I have stored this one output complete in the object is ANOVA. Now take the summary of this ANOVA. Easily we get see this one. We got this ANOVA table. This ANOVA table. See, we have compared according to the group wise. First group, second group, third group. What is the degrees of freedom? Three groups are there. Three minus sorry n k minus one. There are, why it is coming one? Generally, it should be two, right? Yeah, why? Because the degrees of freedom is k minus one. K is nothing but three groups. Three minus one is should be two, right? Why it is coming one? Uh, how many groups are there? Three, one, right? Let's wait. Dimension, dimension of sample group. Oh, two groups we have. Sorry, dimension is 250 rows and two variables. Okay. I want to see what how many levels. That is factor, right? First day we discussed this one. Factor of sample group, in the sample group observations dollar, not observations group. Run it. And there are three groups are there, right? One, two, three. Three groups are there. But why our ANOVA table is showing 1 degrees of freedom? Generally, degrees of freedom for the groups. How many groups are there? K. The K groups means K minus 1. So how many groups we have here? Three groups, right? 3 minus 1 should be 2, right? Why it is coming 1 here? And then what is about residuals? N minus K. N is 250. K is taking only two groups, sir. Why? Because 248 we got. We did somewhere mistake. Where we did mistake? This is group 1 and group 2, group 3. It's clear, right? Observations S1, S2, S3. We have, right? Clearly, three groups we have, right?
Yeah, Shiva sir.
Sir,
Yeah, we stop and go for the doubt session, sir.
yeah, over, sir. Yeah, over, sir.
Okay, thank you. Yeah.
Just, yeah, it's over only. Just
Ah, okay,
one
no
doubt
problem.
I got. That's it.
Okay, sir.
Uh,
Okay, thank you.
why? Because it's, yeah, with three groups only in the data, but it's showing only two. Why it is? I will run again. Huh? What happened? Why it is considering only two groups? Yeah. I will check this one. What is the error in this here? Okay, but this I will discuss tomorrow if it, why it is error. Okay, don't worry. But myself is get it's like a magic. I mean, I'm also wondering how why it is taking as one. Why? Because the degrees of freedom for the groups, the how many groups are there? So k groups. So if you take k groups, k minus one will be the degrees of freedom. So three groups are there. Three minus one should be two, and then residuals. So residuals will be n minus k, number of observations minus number of groups. So number of observations are 250 minus groups are 3. 250 minus 3 should be 247, but it is showing 248, which means that it is considering only two groups. Okay, it is not considered third group. I will let you know why it is. And this is the sum of squares and mean sum of squares and f value and finally see the p value. So you can consider these values or you may not, but focus on this one. When the p-value is less than 0.05, we can say that the significance identified, which means that so we are rejecting the null hypothesis. We are going with alternative hypothesis that the sample means are not equal. If the p-value is greater than 0.05, then we are saying that there is no evidence to reject the null hypothesis, which means that we are accepting the null hypothesis. All the sample group means are equal. Now here, why we got the p-value is 0.05 above, so we are going with null hypothesis because there is no any evidence we got to reject the null hypothesis. So simply we are going to accept the null hypothesis, which means that all the sample groups are equal. This here one point I will clear it and I will close it within 4:30. So what is that is nothing but in analysis of variance ANOVA, if you accept the null hypothesis, for example, here we got right. So if you accept the null hypothesis, which means that all sample group means are equal. This is no problem. There is no problem at all. Yes, we accept null hypothesis, all sample groups approximately equal, so we don't want to worry about that. But when we are going for rejection of the null hypothesis, that is the sample group means are not equal. If you are going with original alternative hypothesis, then there is a problem. Further analysis we have to do. Many people will stop the analysis by doing ANOVA. So they will compare their data. So once they compare data, then they will say that, sir, the ANOVA I got rejected, I got accepted. My ANOVA table that is over. But that is not the complete way of doing analysis. So when an ANOVA is rejected, the ANOVA table is rejected the null hypothesis. We are going with the alternative hypothesis that sample group means are not equal. But here we have to understand that if the statement is showing not equal, then again we have to go for further investigation that which groups are equal, which groups are not equal. Here we have three groups. So three groups is nothing but maybe first group, second group mean is equal, but not equal with the third group. Or second group, third group, both are equal, but it is not going with first group. This another what it tells is no, if any single group is not equal, it is not coincide with the other groups, it will completely reject the null hypothesis. It will not consider only those. If any one mean is different other than the other group, differ than the others, automatic complete ANOVA will be complete null hypothesis is rejected. So here we have to go for further investigation that which pair of observations or which pair of groups are having common mean or not having common mean, that we have to further investigation by taking pairwise comparisons. In statistics we'll call pairwise comparisons or multiple comparisons, MCT, or post hoc comparison test. So further we have to go for investigation, that is multiple comparison. Multiple comparison is nothing but post hoc comparison test. Okay, further investigation we have to do that investigation. We will use many tests. Done test is there, done net test is there, Tucky test is there. Like that, there are many tests are available to go with pairwise comparison of your data. Okay, that I will show you tomorrow. Here I have taken general data, right? So tomorrow I will take real data. For the real data, same empty case data if you want, we'll go with. So we will compare the average mileage of based on their car gas. Okay, we'll compare and we'll go for pairwise comparisons also. That I will discuss tomorrow. Okay, but here one thing I am also getting wonder is nothing but why this ANOVA table is showing here one. Okay, that maybe I will check with this whether the data is problem. Tomorrow we'll go with original data, then we easily will understand. Okay, this I will rectify why this R code is not under listening my word. See, it is not listening my word. It is giving by itself one. But I have given three values right here. Okay, that's what we will call systems are super idiots. Whatever you get, it will consider. It will not think about whether it is the right way or wrong way. Okay, if I ask to calculate the mean for gender, it will calculate. It will give value. But we have to think about that. Systems are super idiots, right? Okay, fine. Anyhow, so fine. If you have any doubts, you can ask, sir.
Yeah, based on today's discussion, if you anyone have doubts, please raise it so that we go for end up. Yeah, I think Shiva sir, no one is replying.
Sir, in the comments I'm reading,
Comment section.
many
Yeah,
points they mentioned. Yeah, nicely mentioned.
yeah.
Between classes, within classes, error sum of squares. Yeah, fine. Another one way, two way. Yeah, great. So for discussing all this means it takes a lot of time, sir. One way ANOVA, two way ANOVA, and again UNCOVA is there, analysis of covariance, one way UNCOVA, two way UNCOVA, and then this is ANOVA nowadays, but we are going with the AI generation. MANOVA is required, multi-weight analysis of variance. So MANOVA one way, MANOVA two way, and if you have some information, past experience, then we are going with MANCOVA. MANCOVA one way, MANCOVA two way. Sir, the law huge statistics is there, sir. Yeah. May I know, sir, what is the purpose he are mentioning, sir, in the comments? Bandi Venu, sir. Sir, you are asking any question or you are giving clarification to the audience?
I think he's asking sharp doubt.
No, these are the points are not looks like questions, sir. It's clear what sir is given. T test is used for sample size n equal to 30, n is less than 30, other equal to 30. Yeah, fine. Mm, degrees of freedom mentioned. Between classes, within class, some of squares is asking. Sir, if you may I know reason, sir. Otherwise, okay, fine. I don't know why sir is mentioning here.
I think sir, these are the doubts one needed by sir to from you.
Okay. Mm,
We'll inform him you separately to contact.
okay, sir, fine.
Yeah, yeah.
Yes, sir. I mean, do you want all the clarifications, sir? These are all?